So in today's lesson, we're going to finish up one more little component that has to do with electronic configurations. And then we're going to start moving on to molecular structure. Today, focusing on two-dimensional structure. And then in the next lesson, we're going to start putting some theory behind 3D molecular structure. So first, we need to finish off one property of atoms, and it has to do with some of their magnetic properties. So some elements have magnetic properties and others don't. There's a variety of factors that go into making something magnetic, but one has to do with electrons and how they spin. So we know an electron has a charge of -1, and we've been representing electrons with these half spins, spin up or spin down. So the spin up and spin down are more trying to refer to a direction. One spinning in one direction, one spinning in the other direction. So if you have something that has a charge on it and it spins or has some motion, it can create some magnetic property. Now, when you have two electrons together, we've been doing one spin up and one spin down. They both have a charge, but they're spinning in opposite directions. So what essentially happens is those charges are equal and opposite when they spin, and they cancel each other out. So what does that mean in terms of electron configurations and elements, and can we use that to help figure out whether something might have some magnetic properties? Definitely. So there's two terms you should be familiar with. One is called diamagnetic and the other one's called paramagnetic. Diamagnetic means all atoms are ions that have paired electrons or no magnetic fields. So for example, if we wanted to do an orbital diagram for neon, neon has 10 electrons. So if we put them into our diagram, spin up, spin down, that's full, spin up, spin down, full, put in 4, so 5, 6, 7, 8, 9, 10. All of those electrons and all of the different orbitals and suborbitals are completely paired up. So elements where all of the electrons are completely paired up are diamagnetic or have no net magnetic field. If you encounter any atoms that have any unpaired electrons, they're considered paramagnetic. It doesn't matter if there's only one or two or several, you just need one unpaired for it to be considered paramagnetic. So if we did something like boron, where boron has 5 electrons, 1, 2, 3, 4, 5. That one unpaired electron in there leads to a slight magnetic character for that element. More unpaired electrons can lead to more magnetic character. So in the D block, where we find a lot of metals, the D block, we know that there's 5 different suborbitals. You can have several different unpaired electrons throughout that orbital, lending itself to some more magnetic properties, and that's where you'll find things like iron, which we know can have some magnetic fields. So next we're moving on to molecular shape. And we're going to do a good review of Lewis structures. This may or may not be a method that you learned last year in grade 11 for drawing them, but it's a really good way to draw Lewis structures in 2D and eventually in 3D. So if you've never tried this method for drawing Lewis structures, give it a shot. And then we're going to look at some new applications of Lewis structures and some exceptions, things that you would not have seen in grade 11. So first of all, why do we even care about molecular shape? The shape of a molecule is really important to determine how it behaves and what kind of properties it has. So all of these things we know about molecules, such as smells, odors, tastes. If you're looking at targeting of medications, they all have to do with the molecule's shape and how it can bind to receptors, and the properties that it has. So shape is really important in a lot of different applications. To give you an idea, when you look at shape, this molecule we're looking at is carbon tetrachloride, CCl4. If you were to draw it based on your knowledge so far, this is the Lewis structure you probably would come up with. Two dimensionals, and it kind of looks like a plus sign. But in reality, it's not a flat two-dimensional structure. It actually takes on the shape of a tetrahedron. These are all the same molecules here, just slightly different representations. So in real life, it actually takes on a 3D shape. So just looking at the formula or looking at this structure, you can't always predict what the 3D shape will be. So that's what we're going to get to on our next lesson. How do we go from 2D to 3D and why that happens? But for now, we're just going to review first how to draw Lewis structures. If you can't draw two-dimensional Lewis structures, then you won't be able to move on to the next part with three-dimensional structures. All right, so we're going to do an example with carbon dioxide. You'll need a periodic table handy, so if you don't have one out already, I would strongly recommend grabbing one, and then we'll get started. So if I wanted to draw the Lewis structure for carbon dioxide, the first thing I'm going to do is figure out how many valence electrons need to appear in my structure. So I've got two elements here, carbon and oxygen. So carbon. Carbon is in group 4 on the periodic table, so that means it has 4 valence electrons. When I look at my formula, there's only one carbon atom. So in total, the carbons are contributing 4 valence electrons. Then I'm going to do the same thing for oxygen. Oxygen on the periodic table is in group 6. So it has 6 valence electrons. This time, though, there are 2 oxygen atoms, so I need to multiply by 2. And all of the oxygens give me 12 valence electrons. And I add them together, and I get a total of 16 valence electrons. So when I draw my diagram, I need to make sure I can count 16 electrons in the bonds and lone pairs. The next thing you want to do is start thinking about how you're going to set up your structure. There's an atom that goes in the center and one that goes on the outside. So there's a couple ways you can do this. One rule says that the lowest electronegativity value for the elements involved will go in the center. So that's one option. This one should almost always work for you. But there's also another way you can do that. This works probably about 95% of the time. If you look at the formula, about 95% of the time, the element that comes first in the formula will be the one that goes in the center. So here we're talking about central atoms. This second little shorter rule that works most of the time, it falls apart usually when there's a hydrogen involved. There's a lot of formulas where hydrogen's at the beginning, like some acids. So hydrogen will never go in the center. You might want to make a little note here. Not hydrogen. Hydrogen can't go in the center. So what does this mean? Carbon, if we look at the formula, it's the first element there. It's going to go in the center. And we can even check its electronegativity value. It's a smaller electronegativity value than oxygen, so that also agrees. And then the oxygen, therefore, is going to be your outer atom, your terminal atoms. So they're going to go on the outside, and carbon's going to go in the center. So step 2 is more just a check before you start building your molecule. How am I going to set it up? What's going to go where? So you know how to proceed going forward. Then what you're going to do is start to build the structure. So you're going to draw a skeletal structure joining the central atom to the ones on the outside, and they have to be joined by at least a single bond. So carbon goes in the center. And for now, it's not a big deal if your structures look a little bit different, but try and spread out the atoms as much as possible. So that means one oxygen is going to go on one side of the carbon, and the other oxygen is going to go on the other. They have to be joined by at least a single bond. So we can put that in right away. And remember, a single bond means two electrons, a pair of electrons. Next, you want to take a mental note. How many electrons do I still have to put in my structure? So remember we had 16 valence electrons. We calculated that in step 1. In step 3 here, I've put in 2 single bonds. That's 2 electrons plus 2 electrons, which means 4 electrons. So I'm going to take away 4 electrons from my total. So here my mental check is I still have to put 12 electrons in my structure. So let's just redraw our basic skeletal structure here that we have. And now we have to put in those 12 electrons. So the way that this process works is we have to fill up the octets of the outer atoms and then deal with the one in the center after. We always fill up the ones on the outside first, no matter what we do. So 2, 4, 6. Remember, a single bond means 2, so 8. There's 8 around this oxygen. 2, 4, 6. 8 here, so this has 8. But by putting in these dots, I put in 2, 4, 6, 8, 10, 12. I've used up all of my remaining electrons. So at this point, your structure might do one of a couple things. Everything at this point might have 8 around it when you check, or it might not. So you know the ones on the outside do. But here, if we take a look at the center, there's only 4 electrons around it, 2 and 2. If the central atom does not have 8 around it, it's going to form multiple bonds. If you remember, there's double or triple bonds in molecules, and this is where electrons can be shared. So in this case, we do need to make a multiple bond to make sure that carbon has 8 around it, but this won't happen with all of your examples. So this is what I have so far, and now I need to share some of these electrons. Atoms will try and share evenly. So if we look at the central atom, it has 4 electrons around it. To make 8, it needs 4 more. I have to get 4 from 2 different atoms. So if I do 4 divided by 2, that means 2 from each of the oxygens. So I'm going to steal any 2 electrons from one oxygen, and I'm going to move them in between the oxygen and carbon on one side. And then same thing, I'm going to pick any lone pair on the other oxygen, and I'm going to move it in the center down here on the other side. What that's going to do is create double bonds on both sides. And then I want to still make sure I show those electrons in there, like that. So now when I take a look, if I've shared electrons, everything should have 8 around it. 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and the carbon has 2, 4, 6, 8, so everyone's happy. So let's make sure you can try a couple on your own. So at this point, why don't you pause the video and see if you can do 2, ammonia and formaldehyde. Ammonia and the bromate ion. If you want to try a few more, you could definitely try them and do a quick online check with those, but we'll walk through ammonia and the bromate ion next. Okay, so let's start taking a look at these examples. So we've got ammonia. First thing I need to know is how many electrons I'm working with. So nitrogen is 5 electrons. There's only 1 of them. There are 3 hydrogens. Each hydrogen has 1 valence electron, so 3 total. So that means I need 8 in my diagram. What's going to go in the center? First element is nitrogen. It's also more electronegative um, than hydrogen, but in this case we said hydrogen is never going to go in the center, so nitrogen wins here. So nitrogen in the center, I have to spread out my hydrogens around the nitrogen. And again, doesn't matter if yours looks a little bit different as long as they're joined. So I need 3. Hydrogen has to be joined by single bonds. If you remember from last year, there are a few elements that don't take 8 around them. Hydrogen was one of them. Hydrogen will only have 2 electrons around it. So here, hydrogen, there are 2, 4, 6 electrons that I've put in my diagram. I had 8, so when I do my check, I had 8 electrons. I've used 6 electrons. That means I've got 2 more left over. These outer atoms are already full with 2 electrons because it's hydrogen, so that last remaining pair of electrons has to go on the nitrogen. And now once I've done that, I can check. There are 2, 4, 6, 8 around nitrogen. So that's your Lewis structure for ammonia. Next, let's take a look at the bromate ion. So bromate ion, we're going to do the same thing, count its number of electrons. There are 7 electrons for the bromine. It's in group 7. There are 3 oxygens, and it's in group 6. So I need to multiply 3 by 6. But if you're dealing with an ion, that also affects the number of electrons. So here my ion has a negative charge, which means it has 1 more electron in it. If I had a positive charge here, I would take away electrons. So make sure you check that. So now when I add all of this up, I should get 26 electrons. When you get your total number of electrons, they should always be an even number. So if you have an ion and you forgot to adjust for the number of electrons and it's odd, something's wrong. So always remember you need pairs of electrons. After I do that, I follow the same procedure. My first element is going to be my central atom, and then I'm going to join my other outer atoms. So in this case, it's oxygen. And again, just spread them out as much as you can for now. I've put in 2, 4, 6 electrons. I had 26, so I still have 20 more electrons to put in. So I'm going to start doing that. 2, 4, 6, 8, 10, 12, 14, 16, 18. These are all full with 8. I still have 2 more to put in. They're going to go on the center to make 20. When I take a look here, I want to make sure everything has 8 around it. 8, 8, 8, and the center also has 8. The very last thing that you need to do if you have an ion, make sure you put your square brackets around it and make sure you put on the charge that's there. For ions, they will always have the square bracket. So hopefully that gave you a little review of Lewis structures and how to draw them. Now we're going to look at a few new parts to Lewis structures with some exceptions, which we're going to build on in the next lesson. So, what are some exceptions to some of the rules we've been talking about? First one's called a resonance structure. A resonance structure happens when there's more than one possibility for drawing the Lewis structure. And what ends up happening is the actual Lewis structure for that molecule will actually be an average of the 2, or even there might be 3 resonance structures possible. So let's take a look at an example so you can see how this works. We've got sulfur dioxide. We're going to count the number of electrons sulfur dioxide has. Sulfur's in group 6. There's 1 of them, so 6 electrons. 2 oxygens. They are also in group 6. So that means in total, sulfur dioxide should have 18 electrons. If I start drawing my diagram, like I've been doing, sulfur in the center, oxygen on the outside, I'm going to start putting in my outer electrons. I've put in 2, 4 so far. So that means I've used 4 of my 18. So 14 left. 2, 4, 6, 8, 10, 12. Outer ones are full with 8. My last 2, 14, go on the center. Now when I take a look here, I've used up all of my electrons, but not everything has 8 around it. My 2 oxygens have 8 around it, but the sulfur only has 6. 2, 4, 6. So what's going to happen? You have to share some electrons and make a multiple bond, but this time we only need 2 to be shared. Which electron's going to give them up? The one on the left or the one on the right? This is where the idea of resonance comes in. So let's say the one on the left decides to share. It's going to move its 2 electrons down there, and your Lewis structure will end up looking something like this, where you have the double bond on the left-hand side. But what if the other oxygen decides to share? What if it says, no, I'm going to share one of my pairs? That's also possible. So what you'll get is a Lewis structure that looks like this. Now looking at it, you might think those are the same things, but remember there's 2 different oxygens. They're their own atoms. One atom can share or the other can share. So which one wins? With a resonance structure, they actually both win. They both happen, and they actually alternate between the 2 different versions, and that's where the idea of resonance comes in. They resonate between the 2. So to show their resonance structure, we use a double-sided arrow, two-sided arrow, something like that. Let's make that a little bit prettier for you. It's not the equilibrium arrow, so don't draw the equilibrium arrow in there. It's a two-sided arrow, and this one here shows the resonance. So if you have to draw a Lewis structure where there could be resonance involved, you've got to show all possible structures in your answer. And it won't say this is a resonance structure, it'll just say draw it. And if you see there's an option for resonance, you have to do it. Next type of molecule is one that's involving something called a coordinate covalent bond. They're coordinate covalent molecules. So we've been talking about electrons and sharing and bonds, and we know in bonds electrons are shared between 2 different atoms, and usually one atom and the other atom, they contribute some electrons there. In these types of bonds, only one of the 2 atoms that form a bond actually share the electrons. The other atom or ion does not contribute any electrons in the bond. So for example, if you looked at how the ammonium ion is formed, NH4+, it starts with ammonia, which is NH3, and it adds a hydrogen ion. We just drew the ammonia Lewis structure a couple of minutes ago. So we have that here. The only difference is here we're showing the dots for the electron pairs instead of the single bond line, just to show how the electrons are shared in those bonds. So to make the single bonds between hydrogen and nitrogen equally share 1 electron. Red is for hydrogen, black is for nitrogen. So you can see there's one of each color with all of those bonds. Remember we had a leftover lone pair of electrons on the nitrogen. That pair, if you have an extra lone pair on your central atom, sometimes what will happen is other atoms or ions can come in and will bond with it to make that coordinate covalent bond. So this hydrogen here, it's positively charged, has no electrons on it. It says I'm attracted to that lone pair, that negatively charged pair of electrons. It's going to come in and bond, and here it makes the coordinate covalent bond. That bond there between the hydrogen and nitrogen, that's the coordinate covalent bond. So it's not always obvious to see that this type of bonding happens unless you really break it down into small steps. But if you're wondering, well, how do all the electrons actually get shared and whether it should be equal all the time or not, it's definitely not always equal. So just something to keep in mind. Last part that's going to be new for today, these are ones that have expanded valence shells. So remember last year and even today we've reviewed the octet rule. Octet rule, everything has to have 8 around it. Well, that's not entirely true. So a lot of the simple molecules have to have 8 around it. These ones definitely do not have 8 around them. So if you want to try to see if you want to challenge yourselves, you can pause the video now and see if you can draw the Lewis diagrams for phosphorus pentachloride, sulfur hexafluoride, and xenon difluoride. Yes, xenon is in here. It's a noble gas, so this molecule would be one that's synthetic or made in a lab kind of scenario. All of the central atoms are still the first elements here, so these ones here, they're all going to be in the center, and the other atoms joined around it, but they're going to break the octet rule. So if you want to give them a shot, go ahead and pause, and then we'll walk through these ones together to finish off the lesson. All right, so let's check what's going on. PCl5. If we add up all of the valence electrons for PCl5, we need to put 40 in our diagram. Phosphorus goes in the center, and we need to spread the 5 chlorines around the phosphorus. Right away you can see why this rule is broken. Phosphorus is in the center. There are 2, 4, 6, 8, 10 electrons around it. Don't worry, we'll learn more about that in the next lesson, why it's possible, but that's okay. We've put our 10 electrons in, we still have 30 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. So there's your Lewis diagram for phosphorus pentachloride. If you hadn't tried one of these and now see how PCl5 works, pause it and see if you can do the sulfur hexafluoride, because that might now give you a better idea of how that one works. All right, so let's look at sulfur hexafluoride. Sulfur hexafluoride, if you count up all of the electrons in it, you should have got 48 electrons that you need. So sulfur again goes in the center, and fluorines spread all around by single bonds. 1, 2, 3, 4, 5, 6. Right away you can see sulfur has 6 bonds around it. That means 12 electrons. Definitely breaking the octet rule. Then I still have the rest of my electrons in, 36 left over. We have to put them in, going around like that. And there we go. There's your structure for sulfur hexafluoride. Last one, and this one's always the one that's a little bit tricky because it's really out of the box, is the one with xenon and fluorine. So, xenon and fluorine. First of all, like we said, this is a synthetic molecule that would have been made in a lab or one that's fictitious. It's not something you'll find in nature. Nonetheless, we can still draw a hypothetical Lewis structure for it. So, xenon is in group 8, which means 8 electrons. There are 2 fluorines. They're in group 7. So when we add that together, that means we have 22 electrons that have to go in the diagram. Xenon goes in the center, and the fluorines have to go around. I've put in 4 electrons so far. So in my head, I still have 18 more to put in my diagram. 2, 4, 6, 8, 10, 12. Always fill up the outer ones first with 8. I've put in 2, 4, 6, 8, 10, 12, 14, 16 electrons. That means I've got 6 more electrons to go. They have to go in the center. So you can already see there's 2 here, 2 bonds. Now I'm going to put 6 more. This is going to break our octet rule. When you're putting them around the center, electrons always stick in pairs. So I'm going to put 2, 4, and 6. Don't try and put 3 and 3. They don't separate. Always keep 2s together. If you put 2 pairs on the bottom and 1 pair on the top, that's fine. But always put them together in pairs. Also, don't ever put them in between where the single bonds are because that implies there's more electrons in those bonds. So don't do that. So when you look at this one, where the rule is broken again is around the center. 2, 4, 6, 8, 10. There's 10 around there. So in our next lesson, what we're going to do is take our knowledge of 2D Lewis structures, including these new exceptions, resonance, expanded shells, and so on. And then once we've got a hang of that, put them into 3D. How can we take our Lewis structures and look at their electron arrangements and change them into 3D structures? With your homework, there is a package of questions on VESPR, VSEPR, in the next lesson. There's 4 sheets of them. There's 1 column on that sheet that says Lewis structures. You can draw all of the Lewis structures for those. I'll put up another screenshot online so you can see. But do the Lewis structures only on the VESPR worksheet package. All right. So practice is the key with this. Make sure you have a good understanding of Lewis structures, and you'll be set for the next lesson.